In this video, we will consider the mechanism of reaction by which a halogen reacts with an alkane hydrocarbon to produce a haloalkane and a hydrohalic acid, or hydrogen halide gas. This is a very important reaction in terms of creating feedstocks for organic chemistry because it creates a polar carbon-halogen bond from a non-polar carbon-hydrogen bond. The difference in electronegativity between carbon and hydrogen, remember, carbon at 2.6, hydrogen at 2.2 is only about 0.4, which means we classify it as a non-polar covalent bond, but the difference in electronegativity between carbon and the halogen chloride, because the halogen is more electronegative, is 2.6 to about 3-ish, 3.2, depending on which table you're looking at. So we're looking at a polar covalent bond that has partial positive on the carbon, partial negative on the chlorine. That enables us to do polar reactions where we can use nucleophiles with both pairs of electrons to donate to the carbon and form new bonds displacing the chloride. So we need to consider what happens when we put energy into this system. We have a choice between breaking a carbon-hydrogen bond in ethane, and the carbon-hydrogen bond in ethane is about 101 kilocalories per mole, or a carbon-carbon bond in ethane, and remember the carbon-carbon bond in ethane is about 89 kilocalories per mole, right? Or the chlorine-chlorine bond. And over on the far right here, I reproduced table 3.4 from page 110 in your text that shows the halogen-halogen bond dissociation energies. 38 for the fluorine-fluorine bond, 58 for chlorine-chlorine, 46 for bromine-bromine, and 36 for iodine-iodine. These three follow the trend that as the bond gets longer, it gets weaker, 58 to 46 to 36. Usually the longer bond is the weaker bond because the nuclei are holding the electrons less tightly. Fluorine is an anomaly. It's actually not much stronger than the iodine-iodine bond, and that's because these two atoms are so small that nuclear repulsion starts to come into play. The nuclei are attracting each other's electrons more strongly than the chlorine-fluorine bond, but the nuclei see each other and they're repelling. So that's a particularly weak bond. That has an important consequence in terms of free radical halogenation. You'll notice that the hydrogen-halogen bond strength goes from HF is the strongest, HCl to HBr to HI. You don't see that anomalous behavior in the HF bond that you see in the FF bond because hydrogen is such a small nucleus that nuclear repulsion is really not a factor. And you'll also see that the carbon-halogen bond also decreases from carbon-fluorine to carbon-chlorine to carbon-bromine to carbon-iodine, as you would expect, because the carbon nucleus is significantly smaller. So again, nuclear repulsion is not a real factor. In fact, if you look at the carbon-halogen bond, here's a primary carbon-halogen bond. But if you look at the methyl and the primary and the secondary and the tertiary, they're all around 110 kilocalories per mole for fluorine. They're all around 85 for carbon-chlorine. They're all around 70 for carbon-bromine. And they're all kind of in the 56, 55 to 57 range for carbon-iodine. So whether the carbon is primary, secondary, or tertiary is much less important when you're looking at the carbon-halogen bond than it is when you're looking at the carbon-hydrogen bond, where primary at 101, secondary at 98.5, tertiary at 96.5, and the methyl carbon-hydrate is actually 105, slightly stronger than a hydrogen-hydrogen bond. So you don't see that big difference in the carbon-halogen bonds, and that will also be somewhat relevant as we go forward. So this is from table 3.1 on page 98. This is from table 3.4 in margin notes on page 110. So the bond that's going to break when we shine light is the chlorine-chlorine bond, because 58 kilocalories per mole is much less than either 89 or 101. So what we show is we show light energy hitting that chlorine-chlorine bond and causing the chlorine-chlorine bond to dissociate. And we refer to that as an initiation step. What's happening is we're breaking a chlorine-chlorine bond, form two chlorine radicals, and that creates something that can continue a reaction. This will be what we call a free radical chain mechanism. broken that initial chlorine-chlorine bond, the reaction can proceed many times to produce quite a few moles of the haloethane, chloroethane, and the hydrogen chloride before you have to create new radicals. Unlike pyrolysis, where you're constantly having to continue to add more heat energy to constantly produce new radicals, because both radical recombination and hydrogen abstraction results in the elimination of two radicals. So the initiation step creates the radicals, and it breaks the weakest bond, the chlorine-chlorine bond. This costs us 58 kilocalories per mole. It's 58 kilocalories per mole endothermic. But as we'll see, the initiation step that costs us that 58 kilocalories per mole is not actually part of the overall reaction when we write the balance equation. A free radical chain mechanism requires initiation, but then once you have the initiation step, it will proceed by two or more propagation steps. And this mechanism that we're looking at here, this free radical chain mechanism, is the same type of mechanism that's responsible for chlorine radicals depleting ozone in the stratosphere and creating the ozone hole. There are more steps in the depletion of ozone than there are in the free radical chain halogenation, but it's the same principle. So once you have that chlorine radical, and it reacts with ethane, it's going to displace a hydrogen. And it can do it in one of two ways. Either it can react with hydrogen to form HCl and generate a carbon radical, ethyl radical in this case. Or alternatively, it could react with the carbon, displacing the hydrogen radical to form the chloroethane. So these are two potential reactions. Product. The other which produces the chloroalkane product. They're both propagation steps. In that they both produce a new radical. So no radicals are not removed from the system. Right? There's a new radical that can continue reacting in this form. We look at propagation step 1A, forming HCl, and propagation step 1B, forming CH3CH2Cl. Once you have that ethyl radical, it can continue with the second step, reacting with an additional molecule of chlorine to form the chloroalkane product and regenerate the chlorine radical. Or alternatively, once you have the hydrogen radical, you can react with the chlorine-chlorine bond to form HCl, and again, regenerate the chlorine radical. So we can have propagation step. B. And propagation step. B. So steps A and B in pathway 1, or steps A and B in pathway 2. Both of these reactions, when added together, both of these will add up to the overall reaction, because the fluorine radical that's a reagent in propagation step 1A is regenerated in propagation step 1B, so that would cancel. And the ethyl radical that's generated in propagation step 1A is used in propagation step 1B, and so that would cancel. And our net reaction, if we add these two steps together, A and B, would be ethane and chlorine reacting to form HCl and chloromethane. Exactly the same thing here. The fluorine radical that we use in propagation step 2A is regenerated in propagation step 2B, and the hydrogen radical that's produced in propagation step 2A is used in propagation step B. So again, the overall reaction would be ethane plus chlorine, yield chloroethane plus HCl. One of these mechanisms is going to be more favorable than the other. And to determine which, we need to calculate the enthalpy of reaction for each of those steps. Anytime you have a free radical chain mechanism, it's essential that the propagation steps have to sum to the overall reactions. That's true regardless of how many propagation steps there will be. There must be a minimum of 2 propagation steps because you're going to create a new radical that has to be used as an intermediate. But you'll notice that these reactions, propagation step 1A and propagation step 1B, add up to the overall reaction without including the initiation step. So the initiation step is not part of the overall balanced equation, and this energy of 58 kilocalories per mole that we put in initially to break that chlorine-chlorine bond isn't part of the enthalpy of the overall reaction. So at this point, in order to determine which mechanism is more favorable, we want to compare the thermodynamics of each mechanism. And so it's important to remember from general chemistry how to use bond dissociation energies to calculate the energy of a reaction. So hopefully you remember that delta H reaction can be estimated by taking the sum of the bond dissociation energies of the bonds that are broken and subtracting from that the sum of the bond dissociation energies of the bonds that are formed. The bond dissociation energy, dH0, is defined as the amount of energy required to break 1 mole of a given bond in the gas phase molecule. It takes energy to break bonds. It releases energy to form bonds, so we have the negative sign here because the formation of bonds is exothermic and no negative sign here. So we can estimate the delta H of reaction for each of these propagation steps. By considering which bonds are broken and which bonds are formed. So in propagation step 1A, we are breaking a primary carbon-hydrogen bond, and that costs us 101 kilocalories per mole. And then we are forming a hydrogen-chlorine bond, and that will release 103 kilocalories per mole. So the overall enthalpy of reaction for that step is exothermic by 2 kilocalories per mole. That's a favorable reaction. In propagation step 1B, we are breaking the chlorine-chlorine bond. That costs us 58 kilocalories per mole. And then we are forming a carbon-chlorine bond, a primary carbon-chlorine bond, which is about 85 kilocalories per mole. So that's exothermic by significantly more, because the carbon-chlorine bond is quite a bit stronger than the chlorine-chlorine bond. And you can do that calculation. You can pull out a calculator if you need to pull out a calculator. Which means the overall reaction, which can be taken by summing these two, is minus 29 kilocalories per mole. Assuming I did those calculations correctly. And if we wanted to do the overall reaction, we would simply add up the 101 kilocalories per mole for the carbon-hydrogen bond and 58 kilocalories per mole for the chlorine-chlorine bond. And then we would subtract from that the sum of the carbon-chlorine bond, or sorry, the hydrogen-chlorine bond, and the 85 for the carbon-chlorine bond. And we should get the same answer, right? Over here, we have plus 159 total, and over here, we have minus 188 total, and again, that's 29 kilocalories per mole. So it's a favorable reaction. Both steps are exothermic. Step 1 is only mildly exothermic. Step 2 is significantly exothermic, but it's a good reaction. We expect it to occur. Propagation step 2a, we're breaking the same carbon-hydrogen bond we broke in propagation step 1a, and what we're forming is the carbon-chlorine bond at 85 kilocalories per mole. So this is not an exothermic reaction. This is significantly endothermic by about 16 kilocalories per mole. Because the carbon-hydrogen bond that we're breaking is significantly stronger than the carbon-chlorine bond that we're forming. In the second step, we're breaking the chlorine-chlorine bond, that's 58 kilocalories per mole. And we're forming the hydrogen-chlorine bond, 103 kilocalories per mole. That's going to be quite an exothermic reaction. That's going to be minus 45 kilocalories per mole. And comfortingly, that results in the same minus 29 kilocalories per mole. It has to, because it's the same overall reaction. So if we were to put these on an energy diagram together, we would find that propagation pathway 1, where the first propagation step forms HCl, and the second propagation step forms the alkyl chloride, is significantly more favorable than the other possible pathway. The hydrogen radical is a very high energy species. It's much less favorable to do that. So the energy diagram for this pathway will look like this: a mildly exothermic reaction by 2 kilocalories per mole, followed by a significantly exothermic reaction of 27 kilocalories per mole. For propagation step 1 and propagation step 2. So this is pathway 1. Propagation step 1A and 1B. Versus pathway 2. Where our first step is endothermic by 16 kilocalories per mole. second step, highly exothermic by obviously, the activation energy for pathway 1 is going to be significantly smaller than the activation energy for pathway 2, and therefore pathway 1 is preferred. You'll form carbon radicals, not hydrogen radical, as your intermediate. Carbon radicals are more stable than the hydrogen radical because carbon is a larger atom and that single electron can expand over a larger region. So now that we've established that, we can proceed to look at the other possible halogenations, fluorine, bromine, and iodine, and determine whether those reactions are overall exothermic or endothermic and to what extent they are exothermic or endothermic. And that'll be the subject of